Hello everyone, this is Alessandro Budroni and I'm going to present the paper Making the BKW Algorithm Practical for LWE. This is a joint work with Qian, Thomas Johansson, Erik Mårtensson and Paul Stankovski Wagner from Lund University and University of Bergen. So I'm going to talk about the LWE problem and in particular I'm going to focus on the BKW algorithm that solves the LWE problem. Then I will talk about our contribution on this topic, I will talk about our implementation, and I will give the conclusions. So let's start with the LWE problem. So let m and n be two integers, where m is larger or equal than n, and let AB be a pair such that A is an m times n matrix, where the entries are sampled uniformly at random as integers modulo q, and B is a vector of length m such that, given S a secret vector of length n, where the entries are sampled at random as integers modulo q, and E an error vector, where the entries are sampled according to a distribution Q at random that has a standard deviation sigma, and the length of the vector is m. Then we have that B is equal to A times S plus E modulo Q. So the problem, the search learning with errors problem, consists in finding S given the pair A and B. Why search version? Because there is also the decision version of the LWE problem, which consists in distinguishing such a kind of a pair, LWE pair, from another pair sampled at random from the same space. So, given an LWE instance, we can always transform it unless, given that we have enough samples, so m is large enough, we can always transform it into a new LWE instance where the secret, so the new secret, has the entries that are distributed according to the same distribution of the secret, of the error. This transformation runs in polynomial time and is reversible. So from now on we will assume that the problems are already transformed. The LWE instances we will consider are already transformed. So why we want to study LWE? Some motivation. So first of all, it's a problem believed to be quantum resistant. It's one of the most important problems in post-quantum cryptography. It has many cryptographic applications like fully homomorphic encryption, identity-based encryption. If you look at the list of candidates to the post-quantum competitions run by NIST, a large number of the key encapsulation methods proposed base their security on LWE or on problem derived from LWE. It can be seen as generalization of LPN, or vice versa. LPN can be seen as the binary case of LWE. LPN is a well-studied problem that finds applications in lightweight cryptography. So there are three ways of attacking LWE, of solving LWE. There is an algebraic approach, which is efficient only for very small noise. There is a lattice reduction, the lattice reduction approach, which is so far the most efficient in practice. So the largest LWE instances solved so far are solved with lattice reduction, and it does not require a large number of samples. So this is a benefit of this approach. Then there is the combinatorial approach, which is the focus of this work, and in general it requires a large number of samples, but I'm gonna go back on this later. So when we talk about the combinatorial approach to solve LWE, we talk about the BKW algorithm. This algorithm was initially proposed to solve the LPN problem, so the binary version of LWE, and then it was in 2015 generalized for LWE. It has it can be divided into two phases: reduction phase and guessing phase. I'm gonna talk about plain BKW, which is the most basic idea in this algorithm, and its reduction phase. And then I will talk about more advanced techniques. So the reduction phase in plain BKW consists in performing operations between the rows of the matrix A, and in particular I mean performing sum and subtractions between rows of the matrix A in such a way, and I'm gonna explain it in details later, such that after a certain number of these operations, we will have that the first, say, NT entries of the matrix A have 0 in their components. So the rows of the matrix A prime will have 0 in the first NT components, and then other numbers which are different from 0. Why we want to do this? It's because when we multiply then A prime times S, we have that a big part of the vectors S, so NT entries in particular, are different from 0. Consider that when we perform these operations, we performed equivalent operations also on the vector B, which becomes B prime, and also on the and as a consequence also the error vector E gets modified and becomes E prime. As a consequence, since we add errors, the final vector E prime will have entries that are larger compared to the initial vector E. But if this is not the error is not too large, we basically obtained a smaller version of the LWE instance, where only smaller in size, since only a small number of entries of the secrets are considered, and since it's smaller, we can try to solve it with a guessing algorithm, and the one used so far is based on the fast Fourier transform. And later in this talk we will introduce a new one. So let's have a closer look on the reduction phase. So consider the first D entries of each row of A, and what we do, we sort the samples according to these D entries. In particular, we divide them into categories, and we put in the same categories samples such that they have either the same first D entries or opposite the first D entries. And why we do that? It's because then we can perform summations if they're opposite, or subtraction if they are the same among these rows of A in the same category, and the resulting vector will have 0 in the first D entries. There are two ways of combining, of making these operations. One is called LF1, which preserves sample dependencies, but the number of samples decreases every time we perform this step. And then there is LF2, which keeps the number of samples the same. It can even increase, but it does not preserve sample dependencies. However, in practice, we have implemented both, but in practice we use LF2. After performing T of such kind of steps, we will have that a big number, say NT, NT of the entries of each row of A are put to 0. The error increases by a factor of 2 every time we perform a step. So for every step, the error, the standard deviation increases, and after T steps, we will have that the standard deviation will be approximately 2 power T times sigma square, where sigma square is the initial standard deviation. Initial variance. Now I'm going to talk about a more advanced technique which was introduced in 2015. It's called the lazy modulus switch, and it can be seen as a generalization of plain BKW. So this time, instead of reducing the samples to 0, so instead of reducing the entries of the matrix A to be 0 in certain positions, we reduce them such that they have entries that are smaller than P, factor P, modulo Q in absolute value. So, for example, if we have that P is equal to 2, then it means that we can accept entries like -1, 0, 1 only. If P is equal to 1, then we can accept only entries equal to 0, and this is equivalent to plain BKW. So that's why we say that this is a generalization of plane BKW. However, if P is larger than 1, it takes less effort to reduce the same number of positions compared to plane BKW. So by less effort, I mean it takes a smaller number of samples are required. However, the reduction has lower quality, and as a consequence, the final error it's larger compared to plane BKW. So the final error is given by the sum of two quantities. One is the same as in plane BKW plus another quantity, and now we see what it is. So a row that is reduced using LMS will have the first empty entries that are small. They are not necessarily 0, but they are small. And when we multiply such a vector against the vector, the secret vector S, we have that part of this multiplication is given by a sum of small values, because we have small values that are reduced by the algorithm and small values of S. And then the second part is given by small values S and values of A prime that are not small. So the sum that is indeed small, it goes and adds to the error. And then there is the rest. So in LMS, we again divide the samples into categories, and then instead of putting samples in the same category, if they have the first D entries the same or opposite, we put them in such a way that when we perform the addition or subtraction, the resulting vector has small values like in these entries. And now I can finally start with our contribution to this topic. So first of all, we introduce a new reduction step, and the motivation of why we did that, I'm going to explain it with an example. So assume Q, the modulo, is equal to 101, M is equal to 12,000, and assume we want to reduce D equal to 3 positions. If we pick P equal to 2, then we have 8,000 categories, and the category capacity, so how many samples fall into each category, is in average 1. And it is not okay, because if we have one sample in each category, we cannot perform subtraction or sum between samples, and we cannot basically perform the step. So the next choice is to pick P equal to 3. The number of categories in this case is 2,744, and the category capacity is 4. So in this case, we have to pick P equal to 3. And this is the only choice we can make. That's not the only, but the most efficient choice. With 4 samples in each category, we can obtain at least 4 more samples, and so the overall number of samples stays constant. However, this is the most efficient choice we can make, but is not the most efficient choice possible, because we only need 3 samples in each category to keep the number of samples, the total number of samples, constant. Because from 3 samples we can obtain 3 new samples, and having 3 samples in each category, where the total number of the category is 2,744, we would need 8,232 samples, and this is smaller than 12,000. So it means that this means that we made the best choice we could make, but this is still not the most efficient choice. So that's why we introduced Smooth-LMS. In Smooth-LMS, we try to build the things in such a way that we use all the samples we have. So we use all the resources we have. In Smooth-LMS, we reduce the first D positions of the samples exactly as in LMS, and if we have more resources left, we reduce 1 additional position. The difference is that this additional position is less reduced compared to the first D. But then in the next step, we take into consideration that these positions are already a little bit reduced, and we make sure that after this step, everything all the entries are reduced in the same way. So in this way, thanks to this trick, we can reduce one additional position in one step, and in practice this allowed us to solve larger LWE instances. The second original contribution of this work is a new guessing method for the algorithm, and in this case is based on the fast Warschademann transform. So what we do is the following: we multiply the system times 2 modulo q and the LWE equation. So we obtain from B a new vector B prime, from A a new matrix A prime, and the error becomes from E, it gets multiplied by 2, it becomes 2E. Then we reduce all the entries of A prime using, for example, Smooth-LMS, and we get new vector B bar, A bar, which is the matrix which is all reduced, times S plus 2 times E, where E is the final noise. At this point, we reduce the system modulo 2. So we get a binary system. B0 is the vector or the binary, the least significant bits vector of B bar. H0 is the matrix of least significant bits of A bar. S0 is the secret, the least significant bits of the secret S. And then there is E, which is a binary error. So we are exactly in the case of an LPN problem. So we transform the LWE problem into an LPN problem. So what is in this case the error E? So if we have that the sum of the row times the secret given by the row times the secret plus the error, if this sum is smaller in absolute value than Q half, then the error is equal to 0. In this case, we have simply a linear system, a linear binary system, and we can use Gaussian elimination to retrieve S0. Otherwise, if the error is not equal to 0, and we have exactly an LPN problem. And then if the error rate is not 50-50, 0 or 1, then we can apply the Warschademann transform to recover S0 equal to S modulo 2. Note that again, if we find S0, then we can consider the problem broken, because given S0, you can retrieve with less effort the whole secret. Looking at the algorithm in total, what we do in practice, we perform some smooth plain BKW steps, where smooth plain BKW is essentially plain BKW plus we reduce one additional position, like we do in Smooth-LMS. Then some Smooth-LMS steps. Then we perform the multiplication times 2 modulo q. Then more Smooth-LMS steps. And then we reduce the system in binary, and we apply the fast Warschademann transform to retrieve the binary secret. The complexity of this algorithm is given by the sum of all these operations. And the expression you see here is the condition on the samples, the number of samples to perform the algorithm. And D is the statistical distance between the final noise of the error and the uniform distribution. So in this table, we compared the estimated complexity of our algorithm against lattice enumeration, lattice sieving, and we see that when the noise increases, so these parameters alpha characterize the noise because sigma is equal to alpha times q. So when alpha increases, the noise increases, and then we see that for larger noise, our algorithm works better in practice than better in theory than lattice sieving, lattice enumeration. Of course, we assume that we have enough samples to perform the algorithm, while sieving, lattice enumeration, they do not require all these samples. Let's have a look at our implementation. So we implemented the algorithm, we implemented BKW for LWE, and we released it as an open source library on GitHub. It's called FBBL, which stands for Fail-Based BKW for LWE. It has the main characteristic of using a fail-based sample storage. So instead of having all the samples in the RAM, we write them into files. Then we use the RAM to read a chunk of them, modify them, and then write them back in files. In this way, we are limited in memory only by the physical memory of the machine and not by the RAM. And so since the physical memory is in general much larger, we can afford to handle many more samples. We implemented plain BKW, LMS, Smooth-LMS, and encoded BKW, which is another step I haven't mentioned in this talk. We support the two guessing techniques based on the fast Fourier transform, the fast Walsh-Hahnemann transform. We were able to solve relatively large LWE instances, and to the best of our knowledge, this is the first implementation of BKW that solves such large instances of LWE. And we supported sample amplifications. I'm going to explain what it is in a second. So we performed two kinds of experiments. One kind is we took some parameter choice and we generated our own LWE instances with as many samples as we needed, and we tried to solve them. So the numbers you see here are not really indicative because the focus of these experiments was to make a proof of concept that the algorithm works in practice. So these numbers can definitely be improved, and there is large room for efficiency improvements. The second kind of experiments consisted in taking LWE instances with a limited number of samples, and then combining these samples as pairs or triples and sum them, subtract them together to generate new samples. Of course, taking into account that these new samples generated will have a larger noise. So the experiment I'm reporting here comes from the LWE instance comes from one of the instances of the TUR Darmstadt LWE challenges, and where the number of samples is limited to be n square. So in this case, 1,600 samples. So we generated with sample amplifications more samples, and we solved it. So this is a proof that it's not necessarily true that the BKW algorithm can be applied only where a large number of samples are provided. So given our conclusions, we introduced a new reduction algorithm in BKW, which is Smooth-LMS, and it's more efficient than LMS. Then we introduced a new guessing technique. We released our implementation as an open source library, which is available on GitHub. So thank you for your attention.